Welcome to the AI4EU Café for live presentations around AI. And the speaker next to me is today Iker Esnaola, coordinator of the artificial intelligence in Tekniker. And he soon will get the moderator role, but meanwhile we're waiting that everybody comes into the cafe. His talk will be today on artificial intelligence for making products and solutions smarter. My name is Carmen McWilliams, and I'm the moderator and organizer of this cafe. I'm the director of the company Grassroot Arts and partner in the European AI4EU project. As always, some small regulations. Please take notice that the session will be recorded. No confidential information shall be shared in this cafe session. In this cafe, the speaker expressed his personal view and opinion. This is not necessarily the official AI4EU project opinion. And for you who may be new, what is this web cafe about? It's an online forum to gain insights into the European AI scene. The idea is that you meet other colleagues, other people involved in AI, and after this cafe you may connect via email. Participants get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research application. And as always, this is an interactive session. You may ask questions to the speaker. On the right side you have a control panel, and you can use it for chat and for asking questions. And please feel free. I will read them later to the speaker. So now we're coming to the main point of this cafe. I shall introduce Iker, and then I give you the mic. Iker holds a computer engineering degree and a master in advanced computer systems, both at the University of the Basque Country, Spain. He received his PhD Cum Laude in computer engineering in the University of the Basque Country, distinguished with the mention of excellence by the Spanish Education Ministry. His thesis contributed to the use of semantic technologies to support predictive analytics processes. He has several publications and workshops, international conferences, and high-impact journals. He has been part of different program committees, and he has participated in many EU-funded research projects. Iker currently is the coordinator of the artificial intelligence in Tekniker and works as a researcher in the intelligence systems unit. So I'm very happy to welcome you here. This is an honor. Thank you that you're here. Hi, Iker. Do we hear you?
Hi, yeah.
Hello. How is it
Hello.
in Basque Country? How is it? So I'm giving you the moderator role.
Okay.
Now you're getting it. Yes. Now you may try to show your presentation. Great.
Can you see the screen now?
Perfect.
Yes. Okay. Okay. Well, thank you, Carmen, first of all, for the nice introduction. I am Iker Esnaola González. I come from Tekniker in Spain, and I will talk about how we use the artificial intelligence to make our products and solutions smarter. So first of all, allow me to introduce my company, Tekniker. We are a research and development center in the north of Spain, the Basque Country. We have more than 40 years of experience on applied research, and we have a multidisciplinary vision that enables us helping our clients in the different phases of the development of new products and solutions. And our mission is to enhance their competitiveness through the technology transfer or the transfer of our knowledge or expertise. We are specialized in manufacturing, but we also work actively and we are experts in other domains, such as the energy, the agri-food, and the health domains. So, hold on. Yeah, sorry. So, well, as Carmen said, I coordinate the artificial intelligence research line. And what we try to do is to incorporate the AI into products and solutions to make them smarter. This AI is introduced in different levels, starting from the lower edge level where we have sensors and actuators, until the more sophisticated systems or solutions. This incorporation of the intelligence is done in an homogeneous way, using of course, the adequate methods and technologies, such as edge computing or machine vision. And how do we see the AI lifecycle in Tekniker? Well, the initial phase is the data acquisition phase. In this phase, the data that will be exploited later on to build these artificial intelligence systems needs to be collected. On the one hand, we have structured data, which may be available in different formats, and on the other, we have unstructured data, such as videos, images, or text documents. These data might come from different elements, such as the IoT devices, or they may also come from external repositories, such as open data catalogs. But in Tekniker, we do not only rely on this type of data to build our AI systems. When we don't have a given data, we can also develop digital twins to generate them. So this data, this simulated data generated by the digital twin, normally represents data that we may not get from real systems, real sensors, or whatever the thing that is capturing the data. So, for instance, if we are measuring the behavior of a given machine component in different conditions, we cannot afford to take this machine to the limit to break the component, only for measuring the behavior and have the data in this situation. So, of course, because if we do that, the machine would break and we would need to repair it, and that would have a very high cost. So that's when we develop these digital twins, and this is when they are necessary. And last but not least, we can also capture the domain or expert knowledge in different ways. So, for instance, formalizing the knowledge of an expert with semantic technologies, such as, for example, ontologies, or also in the form of rules. Then we have the processing and reasoning phase. Here, the data that has been acquired in the previous phase is exploited. It is actually combined with the expertise of the data scientists to generate some models that will later on help solving the problem that we are facing. And of course, depending on the problem to be addressed, different approaches need to be used. So in this case, we can rely on supervised, unsupervised, or even reinforcement learning algorithms. Once we have the model, this model needs to be deployed. Depending on the needs and the possibilities, it can be deployed on the cloud, where we normally have enough computational resources available, on the edge, or somewhere in between what we call the fog. Edge devices have some limitations in terms of memory and speed that have or that need to be considered in the previous phase. And historically, or well, typically, the AI systems were not considered valid for the edge devices, especially because of their performance. But nowadays, thanks to the advancements in the processors such as the NXP, ST, NVIDIA, or also Google Coral, the edge computing is nowadays a reality. And finally, the output produced by these models is used for the decision making. Decisions can be autonomous, or they can also be hybrid. in which the users need to confirm these decisions. And well, the decisions close the loop of this AI lifecycle, and they might be used also as data to feed the models. And all this derives in the smart products and solutions, which can be applied in different domains. To name a few, we have these four: the smart manufacturing, smart energy, smart agriculture, or the smart health. And on top of that, on top of this AI lifecycle, the whole artificial intelligence system that we develop must be trustworthy. And it must be trustworthy by design, which means that a continuous assessment has to be done throughout the whole AI lifecycle. And well, different aspects such as the privacy, the explainability, or even the accountability have to be checked, and the necessary measures need to be enforced to make sure that these aspects are filled. Well, so I'll explain for what I call success stories in Tekniker, how we have applied the artificial intelligence in 4 different domains: in the agriculture, the health, the energy, and manufacturing. And for all of them, we will see the motivation and challenges, the way in which the AI has been implemented to solve these challenges, and the benefits or the results that we obtained. So let's start with the agriculture story. Well, due to the population growth that we will be facing in the next years, the agriculture needs to step up its production. And greenhouses are a good option to do that, because they protect crops from adverse weather conditions, and they also allow a year-round production. However, they are also vulnerable to suffer from pests. The most straightforward solution to deal with this pest problem would be the use of pesticide or insecticides. But of course, the use of these methods can cause adverse health effects, both on the farmers or the people working in the crops and on the consumers. Therefore, there is a need to help farmers in these situations, helping them detecting and identifying these pests that we have just commented. This detection and identification of pests should ideally be done in an early stage, as this could definitely contribute to reduce the side effects of pests in terms of productivity, but also it could help to reduce the use of pesticides. So this help or assistance to farmers should also be provided in a way that avoid the farmers from making all these actions in a manual way, because as you can imagine, it can end up being very hard and costly. And this is where the European project Green Patrol originates. It is a Horizon 2020 project which ended in September, and the goal of the project was to develop robots that could navigate inside the greenhouses while they perform early pest detection in tomato plants. And apart from making this early pest detection, they could also do some control tasks, such as the spraying of the pesticide, in an autonomous way. Well, it's important to note that in this project we targeted 3 very specific type of pests that affect tomato plants. And well, in this presentation I won't go very deep into the positioning solution of the robot, which was also a big part of the project, and instead I will focus on the pest detection and identification. So here we can see the robot that has been developed, how he's checking the leaves. Well, the robot moves through the greenhouses, through the greenhouse, and it analyzes different points of the crop, looking for pests. The inspection is done on both sides of the corridor. So the idea is that the robot makes a route, stopping at certain spots or zones, takes the pictures of the leaves looking for pests, and these pictures are then sent to the cloud, where a model that detects and identifies this pest is deployed. And then it goes to after the robot does this task, it goes to the main station where the batteries are charged. And after that, based on the pests that the robot has detected, it receives a strategy which consists on the point where it needs to go and the quantity of insecticide that it needs to spray. Then the next day, this process is repeated based on the zones where the pests were detected in the previous day. So the robot goes to nearby spots to check whether these leaves are already infected or not. So the question would be, how are all these things achieved? How can the robot know where to look, or which are the pests that the plant has, or where does it need to go to spray, the quantity of spray? How does he know all this? Well, this is where the artificial intelligence comes into play. In this project, 2 different AI systems were developed. Well, more specifically, they were machine vision models based on deep learning, and one of them was for the leaf detection and another one for the pest detection. The first AI system regarding the leaf detection, it's a model which performs a real-time leaf detection, and since the information needed, or since this information is needed in real time, the model has been deployed on the edge. When the leaf is detected, the distance between the leaf and the robot arm is calculated, and the arm gets closer to the leaf so that it can take a better picture to later on identify the pests. Okay. Here it's important to note that the robot arm cannot get too close to the leaf or even touch it, because otherwise it could help to spread these pests throughout the crop. And the second AI system is the pest detection model, which makes an offline pest detection and identification. In this case, the pest identification is done in the cloud, because it's not necessary to do it in real time, and a transfer learning approach has been used instead of training a model from scratch. And this is the pipeline that has been followed for developing this pest detection model, and as you can see, it has 7 different modules. So the first one focuses on the generation of data sets or images that will be used by the model to be trained. And in this case, since we didn't have open source data sets available, we took manual pictures on the one side from a cultivation chamber, and on the other from different greenhouses. Then we have the labeling of the images. Once we get the images, we need to identify which are the pests detected. This is a manual work, and well, as you can see in the video, we used the label IMG tool to make it easier for the experts. After that, the data, well, some data augmentation techniques were applied. This data augmentation consists on different transformation of labeled images, and the idea is to generate variable images that could then help the model to be more accurate. So there are some transformations, like for example, the blurring an image or randomly changing the contrast or the brightness of the image. Then an architecture for the adequate object detection has to be selected. And in this case, the TensorFlow library was used. Both the faster CNN and the SSD were analyzed, and although the faster RCNN is slower than the SSD, a higher accuracy is achieved. So this is why for the pest detection model, the faster RCNN was selected, because in this case, there was no need to make the identification of pests in real time. As for the leaf detection model that we commented earlier, we selected the SSD because we needed a higher speed. Sorry. And after that, we have the hyperparameter selection. We need to fine-tune these parameters to make an accurate model. Then we have the training of the model and the evaluation. In this case, where we split the data in 70-30% for training and for testing. And once we obtained the results, we went back somehow to try to fine-tune even more the hyperparameter selection so that the model developed was more accurate. And what did we achieve with this system? Which are the benefits of the green patrol? Well, as we said, greenhouses are a good option for producing food all year round, but they are also they are an ideal scenario for spreading pests throughout the crop. And if they are not detected on time, they may cause losses up to 15% of the potential income. So with this, with Green Patrol, since we can make the early detection of the pests, we avoid this loss. The system that has been developed, the pest detection, is much more accurate, and consequently the quantity of spray and points where it needs to be used is much more precise. So the use of the pesticides is also reduced, which has a direct effect on both the greenhouse operators and on the final product. And finally, this whole pest identification and treatment is completely autonomous, which lets the operators focus on other important tasks. So this was how we have used the AI for optimizing the food production in greenhouses by, as I said, enabling the early detection and treatment of the pests. And let's see now a use case for the health domain. In this case, a system for point-of-care tests. So continuing with the challenges associated to the population growth that we saw earlier, not only agriculture, but also the health domain needs to be improved, as the increasing number of patients can definitely saturate the healthcare system. So to minimize these saturation rates, some monitoring tasks that are a routine could be made by patients themselves at their homes. And a clear example is the OAT treatment, the oral anticoagulation therapy treatment. The OAT is vital for the prevention of mortality caused by thromboembolic events, such as the brain strokes. And to avoid these health systems, it is necessary for the patient to maintain the appropriate levels of blood coagulations. It is estimated that around 2% of the people in developed countries are under OAT treatment. So this may give us a clear view of the saturation rates that can bring to hospitals and healthcare systems in general. So, well, in the OAT treatment, the INR level of the blood is measured. The INR is the international normalized ratio, and once this INR level is measured in the patient, the doctor establishes the corresponding dose of the medicament that the patients need to have. It is somehow similar to the monitoring of blood glucose by people suffering from diabetes. But of course, for enabling this self-monitoring of INR levels, some specific systems have to be developed. And the development of these kind of systems could also improve the quality of life of the patients, so that they wouldn't need to go to hospitals so often to make this INR monitoring. These systems nowadays they exist, they do exist. However, they are hard to carry, they are difficult to use, and at times they are not as precise as they should be. So it would be great if it were a system that solves this situation with a compact, quick, and easy to use solution. And this is exactly the objective of the Microiron system developed by the I-Line microsystem. It enables the monitoring of the INR levels of the patients with this device that you can see here in the left side. And the good part is that it's inexpensive, it's totally affordable, it's compact, and it is quick. It is suitable to be used both by patients themselves for self-testing, but also by healthcare providers. And it has the CE marking, which well, demonstrates this system's conformity with the health, the safety, and the environmental protection standards to be sold in Europe. And as I said, it is easy to use, as you can see in this image. The patient just needs to make a small prick in the finger to get a blood drop, and then this blood drop is put into this little chip that you can see here, which is used by the Microiron system. The chip aspirates the blood, then the Microiron system calculates the INR value, and it gets the result within a minute. The efficiency and the quality of the INR tests is equivalent to the classical laboratory tests, but it provides the advantage of being a rapid diagnostic test. So how is this possible? How can the Microiron system calculate the blood INR level? Well, once again, this is where the artificial intelligence comes into play. So the Microiron system is based on the microfluidic lab-on-chip technology, and this technology enables embedding several laboratory operations into a single chip on a very small scale. It is the same technology used for the chips that enable the PCR testing for the coronavirus. So as you can see in the image, the chip aspirates the blood, and it goes through these microfluidic channels. The artificial intelligence system monitors the speed, the acceleration, and the position of the fluid until it coagulates, and calculates the corresponding INR level. But this is not as simple as it may sound, because the blood, for example, does not advance with the same speed in the curves of the channel, and well, it's not an easy task. And here in the video, as you can see, well, the blood is being coagulated little by little until its speed decreases and stops. So, well, this was the Microiron system developed to calculate the INR level of the blood, which will then be used by the doctors to calculate the dose that the patients need to take to ensure an adequate OAT treatment. One of the main advantages of this system is that it only needs a blood drop instead of a whole blood tube sample that is needed for making the test in laboratories, which is very, very convenient for the patient. And also the result times are reduced compared with these traditional methods. In a laboratory, it would take hours, even days, to get the iron level, and with this system, it only takes 1 minute. This is also a very positive aspect because it may allow doctors to make a quick check of the iron level of a patient and take the necessary actions immediately. Well, since the patient can self-monitor themselves their iron levels, and the way of using the system is very simple, the test can be done 1 or even 2 times a week instead of once every 4 or 6 weeks as it used to be done in hospital. So the monitoring is much more precise. And all this helps to increase the TTR. The TTR is the time in which the patient has their blood coagulation in a controlled range. Okay, so with the traditional systems, since the monitoring of the iron levels wasn't done so often, the TTR percentages were between 30 and 60%. And with the system like the Microiron, the TTR percentage can go up to the 90%, which is a considerable increase. Well, we have seen another success story, in this case, how artificial intelligence has been implemented on the edge to solve a problem or a situation in the health domain. And now let's see another application of the AI, in this case, in the energy field. So, well, unfortunately, all this coronavirus situation has put our healthcare systems to their limit. And you probably have heard that they say that we need to flatten the curve of infected people. But just in case, what does it mean? What does we need to flatten the curve mean? Well, it means that if the number of infected people surpasses our healthcare system capacity, we won't be able to provide the adequate attention to these patients. And that's why we need to keep the curve below our healthcare capacity limits. Well, this very same situation can be extrapolated to the energy domain. So if we don't keep our energy demand below our energy providers' capacity, new generation plants need to be deployed to address this demand, which has a very high cost, and it has a big and undesirable impact on the environment. And that's why we need to change the energy consumption habits to reduce demand peaks and allocate our demand to other non-peaking periods, and also to maximize the use of the energy coming from renewable sources. And this is where we find the Respond Horizon 2020 project. It is a project that it ended in September, and try to reduce the demand peaks, maximize the exploitation of renewable energy, and in general achieve more energy efficient neighborhoods across Europe. The way in which these goals were targeted was with demand response programs, and demand response programs can be understood as strategies that concentrate on shifting the energy use to help balancing energy supply or demand. In other words, demand response programs try to make the users modify their energy consumption habits. But as you may imagine, this is not straightforward, and even less in the residential sector, where the incentives are not as significant for the dwellers as it could be for example, a big industrial company. Well, so in fact, achieving these energy efficient neighborhoods is a complex multi-objective problem, which has been addressed with the AI. In response, we have defined 4 blocks, and the seamless interaction among these 4 blocks allows the achievement of these energy efficiency goals. So, first of all, we have the measurement block, which focuses on collecting all the relevant data. All this relevant data includes for example, the energy consumption of the dwellers or the energy produced by renewable energy sources, such as PV panels or other systems that provide the energy to the neighborhood. Secondly, we have the forecasting block. In this block, we have 2 services which exploit the data collected in the previous phase. On the one hand, we have the production forecasting, which predicts the energy to be produced by the renewable energy sources that provide energy to the neighborhood. And on the other, we have the demand forecasting, which predicts the energy to be consumed by the whole neighborhood. The third block is the optimization block, which considers these 2 predictions that I have just mentioned, as well as other relevant elements such as the energy prices or also the demand response events, which are events that could be sent by an energy aggregator, for example. And based on all these inputs, it calculates the optimal profile or the optimal demand curve. And what is this curve? Well, it is the demand profile that the neighborhood should follow to ensure that all the goals, all the energy efficiency goals that we have mentioned before are achieved. So, for example, to ensure that there are no demand peaks or that the exploitation of the energy coming from renewable sources is maximized. It is important to note that in the optimal curve, the total energy to be consumed is the same as in the demand forecasting. However, this energy consumption is shifted in certain moments to achieve the objectives that I mentioned. But how can we achieve now this optimal curve? Well, this is where the 4th and the final block of the artificial intelligence system comes into play, the control block. Here, the optimal profile is translated into specific control actions that need to be implemented. In other words, the control block defines the control actions that must be implemented to achieve the desired optimal profile. These actions can be automatic or they can also be manual, where the dweller has to implement certain actions. And for these later type of actions, the user receives notifications in the mobile app that has been developed in the project. So, for example, a dweller may receive a notification saying, "Put your dishwasher at 5 p.m. tomorrow because it's the best time to do it." Well, I won't go into much detail on how each of these services or blocks have been implemented, but I just wanted to mention that well, in the forecasting block, machine learning models have been used for making the predictions. In the optimization block, obviously, optimization models have been used. And in the control block, we have developed a heuristic optimization model, which was used to translate the optimal neighborhood curve into specific individual actions that had to be implemented by dwellers. Oh, and well, all the predictions, the optimization, and the control actions have been done with a horizon of 24 hours. What I mean by a horizon of 24 hours is that the predictions are made for the next 24 hours, the optimization too, and the notifications are sent with 24 hours of anticipation. And well, the part that I will explain a little bit more, because I think it's interesting, is the demand forecasting service. So This demand forecasting service, as I said, is in charge of predicting the energy that is going to be consumed by the whole neighborhood. And this forecasting, or this forecaster, is a data-driven model based on the KNN algorithm. Well, in fact, it's not the typical KNN algorithm, but it is a variant that which is based on the patterns instead of the features, because we saw that it worked better for the energy consumption prediction. Well, under normal circumstances, the performance of the forecasting models may degrade over time because there has been a change that somehow violates the model's assumptions. This is a known fact. This is something that is called a concept drift. And the most common way to deal with this concept drift is the retraining of the model, which consists on training a new model using the same process that was used for the initial model, but this time using the new data available. However, the unusual change of daily habits that derived from the coronavirus pandemic and the confinement measures made this retraining, let's say, strategy not good enough, because the performance of the forecasters wasn't good enough. So in this case, we had to use different strategies, such as, for example, training the models only with the confinement period data, and to try to make again accurate predictions. So we tried different strategies to train the models. Well, of course, the case of the coronavirus made very abrupt changes, and it's something exceptional. But there are also other situations that may happen more frequently that make these changes on the electric consumption of a house. So, for example, when a baby is born or a family member leaves the house. So the identification of the concept drift in this sense and in this scenario is something very relevant. And well, which have been the results or the benefits that we have obtained with the Response project? Well, thanks to the solution that we have developed and implemented in 3 different pilot sites, we have achieved an increase of the 12% of the exploitation of energy coming from renewable sources. So we have achieved this maximization of the energy coming from or of the renewable energy. We have also reduced the dependency of the energy coming from the grid in a 20%, and we have also achieved to reduce demand peaks in up to 50% of the times. Okay, so this was the energy success story, and now let's see the final success story. In this case, the manufacturing domain. So the critical equipment failures are something that the assets that are critical for a machine, they need to be maintained. Some maintenance strategies need to be implemented in these assets, because if these assets break down, the whole machine breaks down, and some terrible losses are caused. Normally, they resort, or companies resort to a preventive maintenance, which ends up being in the premature maintenance of the machines, which is not accurate. I mean, the equipment is the maintenance task for the equipment are implemented too early, so that there are significant costs associated to that. And in this regard, the analysis of particles and the debris dragged by the lubrication of oil machines is one of the most interesting methods nowadays, because it provides an early and detailed information of the beginning of a machine failure. So the correct analysis of the oil could help ensuring that on the one hand, machines are operating within their optimal conditions, and on the other, to anticipate machine malfunctioning or breakdowns by applying timely maintenance actions. This way, also extending the useful life of different components or equipment and minimizing the costs. Besides, if this oil analysis is made online, the analysis results can be obtained earlier, and the human errors that may happen when an operator takes an oil sample, for example, are reduced. And this is where Attentus oilware appears. Well, Attentus is let's say a spin-off of Tekniker, and this oilware sensor is a sensor that can be easily installed and integrated in the machine that we want to monitor. Okay, it is highly sensitive, as it can detect particles and debris as small as 4 micrometers, and most importantly, it provides a way for monitoring the oil conditions online. This way, we avoid the classical method of making an operator go and take an oil sample from the machine and sending it to the laboratory for its analysis. And thanks to these advantages, machine failures can be detected and identified in an early way. The necessary corrective actions can be scheduled in a timely manner, and we minimize all the costs that derive from an inadequate functioning of a machine. And once again, the main driver of this system is the artificial intelligence. So the oilware sensor is installed in any machine, or it can be installed in any machine that uses oil lubrication for its functioning, and it somehow makes a bypass in the oil circuit. A LED provides light, and a camera takes pictures of the oil status. And afterwards, these pictures are analyzed by an AI system which is implemented on the edge. So, first of all, the particles and the debris are identified. It is important to note that the oil may also contain bubbles, and so the bubbles need to be differentiated from the particles. Secondly, these particles are classified according to their size and their form, which will later on enable or allow identifying the status of the oil. And then this status of the oil, or somehow the oil is classified according to the status, which can be done according to different standards, such as the ISO 4406 or the NAS. And finally, the identification and the count of these particles helps determine which is the root cause of these particles, or, well, in other words, what is causing the appearance of these particles, which could be, for example, the fatigue of a component or the sliding wear. So here we can see one of the images captured by the sensor and how the AI system differentiates between a bubble marked in orange or a particle, which is marked in blue. Well, these particles here look small, but they are even much smaller in reality, as they can identify particles of 4 micrometers. And well, just in case, these 8 big bubbles are, well, big points are just markers that the AI system is using to make the calibration. They are not particles or they are not bubbles. So there is also a machine learning algorithm used to classify the status of the oil according to the different standards to get to know which is the cause of the oil degradation. And all this intelligence is not deployed in computers with a lot of resources and capabilities. No. Instead, it is deployed on the edge, where we have speed and memory constraints, but despite these constraints, the intelligence has been implemented in a successful way to make this oilware product smarter. And well, which are the benefits of the oilware? As we said, it substitutes the traditional method of taking an oil sample and sending it to the laboratory. It substitutes this method by the online monitoring of the oil status in machines. And thanks to this online and real-time monitoring of the oil, the accurate status of the machines can be monitored. Consequently, the maintenance tasks of machines can be more accurate, can be more timely scheduled, instead of using the preventive maintenance that I mentioned earlier, which have a considerable 25% of the reduction of costs. The identification of the root causes, or of the causes of the presence of the particles in the oil, helps also detecting early failures in machines with an increased rate of 20%. And finally, the reparation costs that derive from the critical failures in machines are reduced in a 10%, which, considering the amount of money that a critical failure might imply, it's a considerable percentage. And well, sorry, okay, so these are the 4 success stories that we have implemented where we have implemented the AI to make the products and solutions smarter. There are many more examples, and well, there are also implementations in other domains, but I wanted to talk, I mean, I don't want to talk about all of them, because instead of a web cafe, it would be, I don't know, a web dinner, web lunch. Maybe we can arrange this with Carmen in the future. And just very briefly, Carmen, I would like to conclude my presentation with some thoughts regarding the AI. The artificial intelligence is there, the capabilities are there, and the possibilities are unimaginable. In this presentation, we have seen how the AI is not limited to the cloud, because nowadays, with the advancement in the processors, the intelligence can be incorporated directly on the edge devices. So, for example, in the health success story, we have seen how this Microiron system allows patients to monitor themselves. And also we have seen in this last manufacturing success story how this oil analysis and detection for potential machine failures can be done on the edge. And another important thing is that the intelligence, or the artificial intelligence, different artificial intelligence systems can be combined to achieve complex tasks. So, for example, the problem that we had in the agri-food case, it wasn't an easy task, and we combined a robot with a model that detects leaves and a model that identifies pests within tomato plants. So we have seen how different AI systems have been combined, and also in the energy use case, we have seen how different machine learning and optimization models can be combined to achieve this complex multi-objective problem that we had which consisted in achieving energy efficiency in neighborhoods. And well, that's all from my side. I would like to thank again Carmen for the opportunity. I think these web cafes it's a great platform to share our knowledge and our opinion, and as we were talking earlier, to get to know what people is doing and also meet new people, and hopefully this can lead to very interesting discussion. So please feel free to ask me whatever you want, or if you prefer, you can email me. Thank you very much.
Thank you, Iker. This was very interesting, and especially the applied use cases. It's great to see this on agrar, on farming, health, energy, and maintenance. It's really great for this cafe because we know now good examples. One example before I let the public speak, is the example of COVID in the health. Do you think what you have now, this Microiron, could be also used for testing? Do you think about this?
For testing the.
Could you make an application also for corona testing?
Yeah, well, actually, the technology that they are using, the Microiron and the PCR tests, in the basis, it is the same technology, so it shouldn't be very far. Of course, the corona situation, it's a whole different thing. The iron, the calculating the iron level of the blood, it's a much more precise thing. It's very studied in the past, and you have some formulas, some mathematic approaches, and it's much affordable in that sense. I think we still don't know many things about the coronavirus. PCR tests are not very precise either. They have quite a considerable error rate, and but yeah, I mean, having the same technological basis, why not in the future? Why not?
It's just I'm just fascinated on the use cases, so that's why I was wondering if you're already planning the next project. So, but let me ask. Here comes Isaac Bilbatua. Thanks for the very nice presentation, Iker. Regarding the health use case, is the machine vision model based on a black box algorithm?
No. Well, obviously, all these deep learning methods or black box algorithms, they work very well in machine vision problems. But in this case, being such an important, a health topic, doctors cannot rely on black box models. They need to know, just in case, let's say that the iron level of a patient is 1 and the system says it's 3, which is terrible. Mm-hmm. So in case these problems happen, the doctor needs some accountability, needs to know where does this number come from. I mean, they cannot just rely, okay, my system says it's 3, so it failed, but it's 3. No. I think that the health domain is they need accountability more than in other domains. And well, I cannot give more details in the model that we have developed, because the device it's under patent, so it's like confidential. We can say that, but no, we cannot afford to have a black box model in such a sensitive use case like the one we presented, because of that, because we are talking about trustworthy AI, and this is a clear example. They need accountability. They need to know why this iron level.
Yes, thank you. And now comes Marta Aramburu, I know we are over time, so whoever has to leave, thank you for being here, but 2 more questions and then we're gonna also end. Marta Aramburu, for the energy prediction case, how was the quality of the data? Due to the special situation from COVID, she wants to understand that better. You said for the energy prediction case, how was the quality of the data due to this special situation from COVID?
Okay, well, the data that we have, well, normally when you want to predict the energy consumption of a house, you need data, you need good quality data, and you need at least a historical data of, let's say, 1 year. Well, in this case, we had some problems. All of this was in the context of the Respond project, and we had some issues with the devices that we were installing in the pilot site. The data quality affects directly to the performance of the data-driven models. So in this case, the data quality was a big issue. We had several gaps, big gaps of missing data, and that complicated quite a lot the information or the process to develop the predictive models. It's true that from one point onwards, we had quite a stability from these devices. We didn't have much information loss, and that's why we could handle this coronavirus situation, because, well, one of the pilots was in Madrid, in Spain, which was heavily affected by the confinement measures. And if we didn't have that information with a good quality, we wouldn't be able to make the accurate predictions, because, as I said, for making models that were able to predict the consumption during this confinement period, we relied heavily on the data from the confinement period. So yeah, the data quality is essential, and having good quality data, is essential. And yeah. So
okay, thank you. So I would say for today it's good, because I see people have to leave. So if you have more questions, that's the key here, please write directly to Iker, or you can also write to me, as you have my email from the invitation, and I forward it to Iker. So just feel free, use the email and get in contact. That's the idea of this cafe, that you basically, if you're interested, you can connect directly. And I wish you a good afternoon, and thank you, Iker. Thank you. This was really great. I was very interested, because it's often needed is what can you use it for? What is the application? What can you really do with it? So thank you for these very, very clear examples. Thank you.
Thank you, Carmen, for the opportunity.
Yes, great. And next week is a new cafe. I wish you all come back next Wednesday at 3 o'clock. And just one quickly, it's this time, it's one moment. Bhagirat Cum Laude from India, not Europe. So we are having a little bit India with us. And his talk will be about artificial intelligence essential for business leaders. Okay. So thank you again, Iker, and see you all next week, hopefully. And bye-bye. Bye-bye.
Bye. Bye.
Bye.